Hey everyone, welcome to Unit 11, our last unit of the year, and we're going to be having two lessons this unit. Our first one is going to cover acids and bases, and our second lesson is going to be covering a very related topic on equilibrium. So again, this is just surface level about acids and bases as well as equilibrium. We won't be getting into too much detail with this because that's more for if you go into the IB Chem route. So we're going to start with acids, and we're going to be giving a little bit of characteristics about them. So acids will taste sour. They will change the color of an acid-base indicator. So you can have, for example, a pH strip. If you put a pH strip in a solution and it turns colors, normally if it turns red, that indicates an acid, and if it turns blue, that indicates a base. So there are also liquid acid-base indicators that can change color depending on the pH of a solution. So acids are going to usually turn this indicator red. They are also strong or weak electrolytes in aqueous solutions. So a lot of the times acids dissociate into water and then they can conduct electricity. So they are strong or weak depending on the nature of the acid. And some examples in everyday life. So citrus fruits contain something called citric acid. Tea contains tannic acid. So a lot of things we eat and drink are acidic in nature. Coffee over here, hello. So don't think that just because, the name acid, you can't ingest it. You definitely can, but the ones that we use in a lab setting, let's not ingest those. So a lot of the times we use hydrochloric acid in the lab or sulfuric acid. Those are the most common ones. Our stomach contains hydrochloric acid in order to digest our foods. Here's a tannic acid in tea. The tannins are what give tea its characteristic flavor. So now going on to a little bit more of a chemical background about what an acid is. So an acid is a hydrogen ion donor, meaning that it can give these H plus ions. Remember, that is a hydrogen ion. It is a hydrogen atom that has lost an electron. It gives it to other molecules. That is the characteristic of an acid. So for example, hydrochloric acid, HCl, dissociates into hydrogen ions and chloride ions in solution. So basically that HCl is an acid because it gives away these hydrogen ions. That is what the definition of an acid is according to specific definitions, which we'll get into in a bit. So in other words, it donates these hydrogen ions to a solution, and a lot of times other things can grab it up, bind to it. So for example, in water, because remember this AQ means aqueous, dissolved in water. So a lot of the times water, H2O, will actually grab up those free hydrogen ions. So they don't exist just, floating around in solution. They bind to water to make something called hydronium, which is H3O plus. So these free hydrogen ions don't actually exist, but they exist bound to water in the hydronium ion. But they are used interchangeably. So if you see H plus in a reaction, if it's an aqueous solution, it really means hydronium. It's bound to water, but that's, a nuance. You can use these interchangeably. So we have our water molecule here, and it combines with the free hydrogen ion, which is represented by this blue molecule here, and it forms the hydronium ion. So actually, I'm going to get rid of mine because now you see it right here. This H3O plus, and it takes on a positive charge now because it has gained a proton, a hydrogen ion. So you can see water now, and it has 3 hydrogens rather than 2. Okay, and so you can see HCl in solution over here. So you can see this is the HCl molecule, but it dissociates into the chloride and the hydrogen ions here, and then water can snag those up to make H3O plus. So since the hydrogen ions immediately combine with water to produce hydronium ions, the full equation for the dissociation of hydrochloric acid and water should be water plus hydrochloric acid produces hydronium plus our chloride ions. Because that hydrochloric acid gives its proton to water. So again, acids are referred to as proton donors, because remember H plus is only a proton. Hydrogen has one electron and one proton, so if it gives away its electron, all it is a proton. So acids are proton donors. Remember the structure of the hydrogen atom right here. And then if it gives away its electron, it is just the proton in the middle. So an H plus is the same thing as a proton. And you can see hydronium over here being created because of the dissociation of the hydrogen ions, and then the water accepts it. Okay, moving on to bases. Bases are going to taste bitter. They feel slippery, and they also change the color of an acid-base indicator, usually turning it blue. They can also be strong or weak electrolytes in solution, depending on the nature of the base. Example of this would be antacids, like Tums tablets. They contain the base called magnesium hydroxide, and the way they work is if you have a sour stomach, that usually indicates too much stomach acid, and so the base will neutralize your excess stomach acid. Also, calcium hydroxide is a common base, and it's used in mortar, the stuff between bricks. That's composed of calcium hydroxide, this brown or gray stuff right here, depending on the color. So a base is the opposite of an acid. Instead of being a hydrogen ion donor, a base is a hydrogen ion acceptor, meaning it takes ions from other molecules. So for example, sodium hydroxide is a very common base. So NaOH, sodium hydroxide, can dissociate into sodium ions and hydroxide ions in water. So NaOH is a base because it can accept protons, and I'll tell you what that means in a second. Okay, so this hydroxide here, this is really what we're talking about whenever we say a base. The hydroxide part is the base part. We don't care about the sodium. It's just a spectator. It's chilling in there. I don't care. It could be anything. It could be calcium hydroxide like we saw before, magnesium hydroxide, potassium hydroxide, sodium hydroxide. I care about the hydroxide. And of course, there's a lot more bases besides hydroxide, but we're just getting into it. That's the most common form you're going to see. So this hydroxide, this OH minus, you can see that it can accept a proton in order to form water, because OH minus, you see we have one oxygen, one hydrogen. Adding one more hydrogen will give you water. So that is what makes it a base, because bases accept protons to produce water. So you can see here, if there is a proton in solution, it grabs it up to make water. So you can see here that some hydronium ions are giving their proton, or the hydrogen ions, because remember, they're really taking it from hydronium because, they're interchangeable in solution, and hydrogen ions aren't by themselves. They're always in hydronium. So this hydronium ion right here is giving its proton to the hydroxide in order to make water. And it produces two waters to do this, because you can see once the hydrogen ion is given, then we have the original water molecule plus a new water molecule that is made. So you can see our two water molecules here. Definitions of acids and bases in terms of proton donor and acceptor are referred to as Bronsted-Lowry acids and bases. So according to this Bronsted-Lowry acid-base theory, an acid is a hydrogen ion donor and a base is a hydrogen ion acceptor. So for example, if we mix hydrochloric acid with water, the hydrochloric acid is acting as an acid because it donates that proton to water to form hydronium. That is what makes it an acid. Okay? The base is the one that accepts the protons. So in this instance, water can act as a base. Remember, anything that accepts protons, according to this theory, is basic. So I know it's hard to wrap your mind around that water can be a base. It can also act as an acid. I'll show you that a little bit later on. So if one substance is acting as an acid, another substance must be acting as a base. They always come in pairs. So if you see an acid, there will be a base somewhere in the solution. So what I want you guys to do, I'm going to do the first one for you. I want you to determine what is acting as an acid and what is acting as a base in the forward and reverse reactions, because we're going to talk about this when we talk about equilibrium. But if you see arrows like this, that means the reaction can happen forward and reverse. And not only that, the forward reaction is happening at the same rate as the reverse reaction. So that is what is known as equilibrium. And a lot of acid-base reactions are equilibrium reactions because they can switch back and forth, right? So we have ammonia here, this NH3, reacting with hydrochloric acid to produce ammonium. Remember, NH4 plus is ammonium, and chloride. So what is really happening? This hydrogen here on the hydrochloric acid is giving its proton to the ammonia. So this is acting as the acid. Then the ammonia is acting as a base. So it's common, well, I don't know if it's common, but some of you might know that ammonia is a base. And the reason it's a base is because it accepts the protons from the hydrochloric acid. So in this case, the ammonia is the base, hydrochloric acid is the acid. So in the second example here, what is happening? We have hydroxide and hydronium producing our two water molecules. We already talked about this. So this hydronium gives its proton to the hydroxide. So this is acting as the acid, and OH minus is acting as the base. All right, so I want you guys to do the same thing for the last three. Identify what is acting as the acid and what is acting as the base. That was the forward reactions, right? Let's talk about the reverse reactions, okay? What if it's going backwards? So in that case, let's look at the reaction going this way. So the ammonium gives its proton to the chloride to make hydrochloric acid. So in this case, if we go backwards, the ammonium is acting as the acid and the chloride is acting as the base. Okay, now the second one is a little bit tricky because, there's two waters, but one of them is definitely giving, I'm just going to the one right here, giving its proton to the other one. So in this case, one water is acting as the acid and the other one is accepting that proton, so it's acting as the base. So go ahead and do this for both the forward and the reverse reactions for the last three. All right, so we talked about the ammonia and water reaction in the last slide. So in the above reaction, we said ammonia was the base, water was acting as the acid in the forward reaction, whereas ammonium is acting as the acid and hydroxide is the base in the reverse reaction. Because again, the acid gives its protons. Okay. So these pairs, if they act as an acid and the other one acts as a base, these are called conjugate acid-base pairs because this is Bronsted-Lowry theory. So Bronsted-Lowry theory, the acid that gives its proton forms a conjugate base. Because this is what happens after the acid gives away its proton. So therefore, the base here, the ammonia, after it accepts the proton, it forms ammonium. So its conjugate acid is NH4 plus conjugate acid. Okay. So the conjugate acid-base pair would be NH3, NH4 plus, and then we have another conjugate acid-base pair, and that would be the water and the hydroxide. So basically it's like how it started and how it ended kind of thing, but they're called conjugate acid-base pairs. So they differ by a proton and are on opposite sides of the reaction. It's basically what forms after the acid gives away its proton or after the base accepts the proton. Okay, so it's showing you basically what I did. So I want you guys to identify the conjugate acid-base pairs in these reactions. Okay, so we're going to talk, I'm going to go back a little bit, about some common acids, and we're going to learn how to name these in a second. But we see hydrochloric here, this is sulfuric, and this is phosphoric acid. So you can see all of them are similar in the fact that they all contain hydrogen, and that is a commonality of acids. They all contain hydrogen because according to Bronsted-Lowry, they donate some hydrogens, right? So whenever those acids donate the hydrogens and they form these anion bases, that is the way that it is being an acid. It is donating that proton. And then it forms the anion or the conjugate base. This can also be true for organic acids, so a lot of carbon-based acids. They can also donate protons, except you don't see it usually at the beginning, you see them at the end. So you see these different organic acids also have these H's at the end that can be donated. So when they do that, they also are acting as acids because they're donating the proton, and then the resulting anion, that is the conjugate base formed. So we have a list of common acids here. So sulfuric, hydrochloric, nitric, carbonic, phosphoric, ethanoic, and methanoic acid. So when it donates its protons, an anion is formed. So the anion, after those two protons from sulfuric acid go away, forms sulfate. So I want you guys to write the name of the anions form when they lose their ionizable or their red protons, right? So this would be sulfate. Okay, the next one, obviously the anion left behind whenever it loses the one proton would be Cl minus. The reason the sulfate is a 2 minus because it lost the two protons, right? It lost its two positive charges. This chloride is only 1 minus because it only lost one proton. So this would be, of course, chloride. That's the name of the anion. So I want you guys to keep going and name the anions formed. And remember, even though these ones are a little bit more complicated, the name of the anion is in the name of the acid, right? So if you see ethanoic, you can kind of think, if it loses it, I bet you that anion is gonna be ethanoate, okay? Because I know you guys aren't familiar with that one, but that's ethanoate. And this one is methanoate. Okay, I want you to fill in the rest yourself. Okay, so how do we name these acids? Okay, so I'm not going to make you guys name like really complicated acids, just the common ones, but there's basically two categories of acid. Those that are binary, which contain hydrogen and one anion, like this one, hydrochloric. And so if you see HCl, basically you know it is binary because I have two elements in it. The first one is hydrogen. So when you're naming it, all you have to do is use the word hydro plus the name of the anion and then add an ic at the end. So HCl would be hydro, and then the anion is chloride, so hydrochloric acid. If you had something like HBr, another binary acid, bromide is the anion, so it would be hydrobromic acid. Or what's another one? Oh, of course, HF, hydrofluoric acid. But if you have more complicated acids, like what if you have a oxyacid? So an oxyacid is basically anything that has hydrogen and a polyatomic anion with oxygen in it. So anything like with sulfate, with carbonate, with nitrate, anything that has more than two elements and an oxygen in it, that would be an oxyacid. So there's two different ways to name these. So this one would be H2SO4. And I know that it is an oxyacid because I have more than two elements, and I know that this anion has an oxygen in it. So I know this is a combination of hydrogen and sulfate. Sulfate. So if my polyatomic ion ends in 8, then all I have to do is name the the beginning part of the polyatomic ion and add an IC at the end. So for example, this is sulfate. So it's not going to be hydrogen sulfate. It's going to be sulfuric acid. So anything with a hydrogen and an ion ending in 8 will just be the name of the anion, put an ic on the end of it. So this is sulfuric acid. And I know it's a little bit weird because sulfate is like sulfic acid. That just sounds really weird. So this one is sulfuric, but I'll give you another example. This is hydrogen with carbonate. So since carbonate is the name of the anion, this acid is just carbonic acid. Or we have H3PO4. So this is phosphate and hydrogen. So this would be phosphoric acid. Okay? If you have hydrogen and a polyatomic ion that ends in "ite," like, for example, sulfite would be H2SO3. Well, so that's hydrogen and sulfite. So if your anion ends in "ite," you don't say sulfuric acid anymore, you say sulfurous. So this is sulfurous acid. So it ends in OUS. Another example would be like nitrous acid, HNO2. So NO2 is nitrite, so that would be hydrogen and an "ite" anion, so it would be nitrous acid, as opposed to nitric acid, which is HNO3, hydrogen plus nitrate. So basically my rule of thumb is this: ate-ic, ite-us. If it's an ate anion, it ends in "ic. If it's an ite anion, it ends in "us." And there you go, that's how you name acids. Okay, also, okay, let me get rid of all this red. Go away. Acids can donate different amounts of protons depending on their nature. So something that can donate one hydrogen ion is called monoprotic because there's only one in the formula. A diprotic acid is something that contains two protons, so it can donate two. Di means two, obviously. And then something like phosphoric acid, H3, it can donate three protons, so it is triprotic. So while some acids can be monoprotic, diprotic, or triprotic, organic acids, on the other hand, can usually only donate one proton. So usually organic acids are only monoprotic. And that's just because of the nature of the molecule. They only have one proton that they can donate. So again, acids that contain only one ionizable hydrogen are called monoprotic, and ionizable just means it can form an ion in solution. So obviously an acid will form a hydrogen ion in solution. So for example, hydrochloric, it's going to produce the hydrogen ion and the chloride anion. Acids that contain two ionizable hydrogens are called diprotic. Again, our sulfuric acid example. I'm going to move my head over here. And then acids that contain three ionizable hydrogens are called triprotic, like phosphoric. So I did want to point out that just because it can donate more protons does not necessarily make it a stronger acid. It's the extent to which that acid can donate the proton that makes it stronger or weaker. So if it likes to donate the protons completely, like for example, hydrochloric acid is a strong acid because it completely dissociates its proton. However, if you have something like phosphoric acid, that is actually a weak acid. So even though it has three protons to donate, it doesn't lose its protons as easily as something like hydrochloric. So don't confuse more protons with stronger. It's not necessarily that, it's the extent to which it can donate that proton. If it donates them much more readily, they are stronger acids than those that do not. So I want you to classify the acids on the previous list as monoprotic, diprotic, or triprotic. So when I'm talking about the previous list of acids, I'm talking about this one, the list of common acids. I want you to identify these as monoprotic, diprotic, or triprotic. All right. So now that we talked about some common acids, we're going to talk about common bases. So the following is a list of common bases. I talked about hydroxides already. Water is also a common base. Remember I said it can accept protons. And then ammonia is also another one. So I want you to write the compound formed after this. Why does that say acid? It should say base. I'm sorry. I have to change that on your notes, but that's base. So the base name, hydroxide. What is the compound formed after it accepts a proton, and what is the name of that compound? So for example, the compound formed after hydroxide accepts a proton is water. What's the name of water after it accepts a proton, and what is the name of ammonia after it accepts a proton? Okay. So remember, hydroxides are also polyatomic ions that are bonded to positive cations. So therefore, compounds that contain hydroxides are bases, because they can accept a proton, because once they dissociate, they become OH minus, which means they can accept a proton. So what is the formula for the following hydroxides? So if you have potassium hydroxide, what is the formula for it? And remembering that hydroxide is OH minus, okay? So I want you to do this for potassium, sodium, magnesium, and calcium. And these are actually very common in everyday life. So sodium hydroxide is also known as lye. It's used to make soaps, and I think it's in drain cleaner as well. Magnesium hydroxide is in milk of magnesia. It's a common antacid. Calcium hydroxide is also known as slaked lime. It's used to like neutralize acidic pools and stuff like that. And then potassium hydroxide is called caustic potash, which I'm actually not quite sure of the common use for, but maybe you guys can let me know. So again, common bases like to accept protons, and they form these, which are now conjugate acids. So now we're going to talk about what amphiprotic means. Sorry, I'm just going to zoom in, go a little bit ahead. Okay, so amphiprotic species are things that can both donate protons and accept them depending on the reaction. So in other words, it can act as both an acid and a base. So I don't know if you guys have caught on by now, but water can act as both an acid and a base. So it is amphiprotic. So when water reacts with an acid, it is acting as a base, but if it's reacting with a base, it's acting as an acid. So it just depends on what it's reacting with. So for example, here we have water reacting with hydrochloric acid, accepting the proton, so it is acting as a base. However, water can also act as an acid. So if it reacts with ammonia, a common base, it is going to donate its proton to ammonia in order to make hydroxide and ammonia. So now what I want you guys to do is practice. I want you to write the formula of the molecule formed when these amphiprotic species both lose and gain a proton. So when they lose a proton, they're acting as an acid, and when they gain a proton, they're acting as a base. So all of these are amphiprotic, so they can both lose and gain protons, but I want you to write the formula of what happens as they act as an acid, and then after they act as a base. So we're also going to practice writing reactions. So for example, the hydrogen sulfate ion, what happens after it already has lost one proton, is amphiprotic. So if it reacts with hydronium, so water, say for instance, you have sulfuric acid and water. So that sulfuric acid is going to donate its proton to water because it's an acid, producing hydronium and then HSO4 minus, okay? But then that HSO4 minus can react with the hydronium ions, and if it does that, it will just reform the acid. Sulfuric acid plus water. Okay, so if it reacts with base, though, instead, it will be an acid, so it will donate again, right? And so this one is acting as a base because it has accepted the proton from hydronium. But if it acts as an acid, it's going to donate its proton to the hydroxide. In this case, it will make SO4 2 minus, right? Because it lost another proton, and then it will make water. So in this case, hydrogen sulfate is acting as both an acid and a base, depending on what it's reacting with. So we're going to identify the conjugate acid-base pair. So again, this hydrogen sulfate in the first reaction is acting as a base. So then the conjugate acid would be the sulfuric acid. And then the hydronium is acting as an acid. So its conjugate base would be water. Same thing here, the hydroxide is acting as the base. So the sulfate, after this acid lost its proton, so this is the base, the conjugate base, and then the conjugate acid would be water because it has accepted a proton from the hydrogen sulfate. So water itself also ionizes. So when I say it self-ionizes, that means it can break apart by itself without reacting with anything in order to produce hydroxide and hydrogen ions. So again, notice this equilibrium arrow because this can go back and forth. So remember, free hydrogen ions don't really exist in solution, but instead combine with water to make the hydronium ions. So we're going to write the reaction actually correctly. All we're going to say is this free ion is going to combine with another water molecule to form hydronium. Okay, so remember they're interchangeable, hydronium and hydrogen ions. So you can see here in water, we could have both hydroxide and hydronium. And we're going to talk in a second, but why water is a neutral pH or pH 7 is because it has a balance of the acids and bases. Because in this case, forming the proton, right? So this is going to, in this case, water is acting as an acid because it's donating its proton. But in this case, water is acting as a base because it's accepting the proton. So there's actually like equivalent amounts of acid, water acting as an acid and water acting as a base. So it's neutral. So therefore, the full equation for the self-ionization of water is going to be water just combining with itself to make hydronium and hydroxide. And again, one of them is acting as an acid, one of them is acting as a base. And for simplicity, we often just write H+, but remember, H+ is really H3O+. And remember, those hydrogen ions are referred to as protons, and don't forget, a hydrogen ion is a proton. It's just one proton. It has lost its electron. So in summary, a small amount of water molecules in any solution self-ionize, split into hydrogen and hydroxide ions, and then that hydrogen ion reacts with another water molecule to form hydronium, so it's more accurately represented as hydronium. Okay, so now we're getting into actually what pH means, okay, on the pH scale. So the pH scale goes from 1 to 14, with 1 being the most acidic and 14 being the most basic. However, you can have pHs that are below this, but we're not going to talk about this right now. But the reason that we have this scale is based on the self-ionization of water. So we have this formula known as Kw. Okay, so Kw is representing the dissociation of water into hydrogen and hydroxide ions. And in water, which is a neutral solution, if we multiply the concentration of hydroxide by the concentration of hydrogen ions by the concentration of hydroxide, we get this number here. 1 times 10 to the negative 14. If you see something in brackets, by the way, that means concentration. And remember, our units of concentration are molarity, capital M. So this represents a neutral solution. Okay, they're not acidic nor basic, and they have equal concentrations of hydrogen ions. So the Kw of water, okay, the dissociation of water, is 1 times 10 to the negative 14, because they have equal amounts of hydrogen and hydroxide ions, so equal amounts of acids, equal amounts of bases. So what is the hydrogen ion concentration of a neutral solution? Well, if you have to know it equals 1 times 10 to the negative 14, right? What is and they have to be equal. So the square root of 1 times 10 to the negative 14th equals, sorry, I'm trying to write that nicely, is 1 times 10 to the negative 7. So hydrogen is going to be 1 times 10 to the negative 7 molar, and hydroxide is also going to be 1 times 10 to the negative 7th molar, and you multiply them together, you get 1 times 10 to the negative 14. Now this, maybe you have a sneaky suspicion as to why the pH of a neutral solution is 7. It does have something to do with this, and I'll get into that in just a second. Okay, so in an acidic solution, you have more hydrogen ions than hydroxide, because the definition of pH, or the power of hydrogen, is basically referencing the amount of hydrogen ions in solution. The more hydrogen ions, the lower the pH. So basically anything with a pH of less than 7 is considered acidic, and anything with a pH of greater than 7 is considered basic. Okay, so if you have more hydrogen than hydroxide, then you're going to have an acidic solution, so more hydrogens. And this is actually a different definition of an acid. This is what's called the Arrhenius definition. Remember, the Bronsted-Lowry definition was that an acid is a proton donor. The Arrhenius definition is a bit broader, and it's saying anything that increases the hydrogen ions in solution is an acid. So just know there's a slight nuance between Arrhenius and Bronsted-Lowry definitions. Remember, Arrhenius, anything that increases hydrogen ion concentration is an acid, whereas Bronsted-Lowry says it has to donate those protons, okay? So hydrochloric acid creates an acidic solution by producing those hydrogen ions, right? And so you're going to increase the concentration of your hydrogen ions in solution, therefore you're going to have an acidic solution. So, and this is just a fun fact, hydrochloric acid is also called muriatic acid. It's what's used to clean swimming pools and stone buildings. So yeah, more you know. So what if instead you have a solution that has less hydrogen ions and more hydroxide ions? That's called a basic solution, again, by the Arrhenius definition. So anything that has more hydroxide than hydrogen in solution, by Arrhenius's definition, is a base. But remember, the Bronsted-Lowry definition is a little bit more specific than that. It says that anything that accepts protons is a base. Okay. So basic solutions are also called alkaline solution, and they produce these solutions by producing hydroxide. So when they dissociate, for example, sodium hydroxide produces hydroxide by dissociating. So therefore, you're going to have more hydroxide than hydrogen ions in solution, which makes it basic. Ammonia creates a basic solution by removing hydrogen ions. So according to Bronsted-Lowry, remember, a base accepts a proton. But according to Arrhenius, it's anything that increases the concentration of hydroxide. And ammonia does this under both definitions. Okay, so anything that's an Arrhenius base is also going to be a Bronsted-Lowry base. Or anything that's a Bronsted-Lowry base, I'm sorry. So anything that's going to be a Bronsted-Lowry base is also an Arrhenius base. It's just like a more specific definition. So remember, in water, we have H plus and we have OH minus, right? So anything that removes hydrogen ions is going to, by default, increase the concentration of hydroxide in solution, therefore acting as an Arrhenius base as well as a Bronsted-Lowry base. In summary, a neutral solution contains even amounts of hydrogen and hydroxide ions, and that amount is 1 times 10 to the negative 7th molar. So don't worry about this. This is IB definition, but you can just say capital M, molar. Okay. An acidic solution is going to be anything that is greater concentration of hydrogen ions than 1 times 10 to the negative 7th. And a basic solution is going to be anything that contains more hydroxide ions compared to hydrogen ions. And remember, again, this H plus is the same as H3O plus. So how do we calculate this? Like, how is this related to the pH scale, 0 to 14? Remember, I said 1 to 14 because most acids we deal with don't have a pH less than 1. Technically, the scale can go down farther, but, so the pH scale is 0 to 14. But so if we want to calculate any of these hydrogen ion concentrations or hydroxide ion concentrations or pH of a solution, it's very simple. And it's all based upon this dissociation of water, right? This Kw factor. So what you have to do is you have to take the concentration of hydrogen ions, right? And you have to use our Kw of 1 times 10 to the negative 14th and just solve for the unknown. All you have to do is divide 1 times 10 to the negative 14th by our hydrogen concentration, which is 1 times 10 to the negative 5th, and that will give you your hydroxide concentration. So that is going to be negative 1.0 times 10 to the negative 9 molar. Okay, so this is our hydroxide ion concentration. And our hydrogen ion concentration is 1 times 10 to the negative 5th. So what is greater, hydrogen or hydroxide? Definitely hydrogen ion is bigger. Because remember, 1 times 10 to the negative 5th is bigger than 1 times 10 to the negative 9th, because we're talking about decimals here. So because this is bigger, Coke is acidic. Okay, it is acidic and it actually has a pH of 5. And are you kind of getting the Hint that the pH is related to this number here, because it is. Okay. So let's do another example. So you guys are going to do this one. So if you know the hydroxide ion concentration of a solution is 1 times 10 to the negative third molar, what is the hydrogen ion concentration in solution, and is it acidic, basic, or neutral? So again, you're going to use this formula, but you're going to plug in the hydroxide ion concentration here and just solve for H. And then tell me, is it acidic, basic, or neutral? Okay, so now we're going to move into the pH scale numbers, the 0 through 14. So it was developed to easily quantify the acidity of a solution based on the hydrogen ion concentration, because remember, pH is power of hydrogen. So it's very simple. A pH is the negative log of the hydrogen ion concentration. You can easily do this on your calculator here. You just have to push the negative and then the log button, put in whatever your hydrogen ion concentration is, and it will give you the answer, okay? So this can also be expressed like, what if you have a pH, but you want to know the hydrogen ion concentration? So the hydrogen ion concentration is 10 to the negative pH. So if you have a pH of 8, for example, your hydrogen ion concentration will just be 10 to the negative 8th. 1 times 10 to the negative 8th. That's all you have to do. So, for example, what is the pH of neutral water? Obviously, the hydrogen and the hydroxide ion concentrations are equal for water, right? So 1 times 10 to the negative 7. So pH equals negative log of 1 times 10 to the minus 7, which equals 7. Okay. Also, our hydrogen ion concentration equals 10 to the negative 7, because the pH is 7, which is the same as 1 times 10 to the negative 7. So we use a logarithmic scale to measure pH. So here is our pH scale, again, 0 to 14, even though we really don't deal with things that are less than 1, unless you're, pretty advanced in chemistry. We don't want to be dealing with acids that are that corrosive. But okay, so the pH scale is an inverse scale. Remember, the lower the pH, the higher the acidity, the greater the pH, the increasing basicity, okay? So this means as the pH value decreases, the hydrogen ion concentration increases. This is more hydrogen ions. This is less hydrogen ions. Okay, so you can see here on the hydrogen ion scale, because 10 to the negative 6th is less than 10 to the 0. Okay, because we're dealing with scientific notation here. So these are really small decimal numbers here, and these are larger numbers here. Okay. So the pH scale is a logarithmic scale. So what does that mean? It means that a change in 1 unit of pH changes the acidity by a factor of 10. So for example, a pH of 7 has a hydrogen ion concentration of 1 times 10 to the negative 7. If we move down by 1 pH unit, going down to pH of 6, we actually increased the hydrogen ion concentration by a factor of 10. So instead of being 1 times 10 to the negative 7th molar, it is now 1 times 10 to the negative 6th molar. So it changes by a factor of 10. So as you move down by 1, it's getting 10 times more acidic. If you move up by 1, it's getting 10 times more basic, okay? Or 10 times less acidic, however you want to say it. And if you move up by 2, that's 100 times more basic. Or if you move down 2 pH units, it's 100 times more acidic, because 10 times 10 is 100. So we can do this to estimate the pH of a solution. So if the pH, if the hydrogen ion concentration is 4.2 times 10 to the negative 6th molar, remember moles per decimeter cubed, that's the same as molar or moles per liter. We can estimate the using the hydrogen ion concentration and the power of 10, the logarithmic scale, okay? So pH okay, so let's estimate first. So we have 10 to the negative 10th. So that tells me the pH is probably around 10, right? Because this exponent is giving you a hint as to what the pH is. But we can calculate the exact pH, okay? So the negative log of 4.2 times 10 to the negative 10th. What's the exact pH? So let's look. Negative log of 4.2. So it's 9.38. So you can estimate just by looking at the exponent what the pH is, but you're going to have to put it on a calculator to actually tell if this number is anything other than 1. Much more or less acidic is this than neutral water? So we remember neutral water is a pH of 7. So going up by a pH unit of 1 to 8, that would be 10 times less acidic, right? Going up to 9 would be 100 times less acidic. And going up to 10 would be 1,000 times less acidic. So we're kind of close to 9 here. So it's about 100 times less acidic. So we can also do the opposite. If we have pH values, we can find the hydrogen ion concentrations, because remember, hydrogen ion concentrations are 10 to the negative pH. So 10 to the negative 4. So it has a hydrogen ion concentration of 1 times 10 to the negative 4 molar. If you have a pH of 11.55, that's 10 to the negative 11.55. So I can't just do that in my head. I have to put that in my calculator. So 10 to the negative 11.55 equals 2.82 times 10 to the negative 12th molar. Okay, so all you have to do is use this equation. You don't have to memorize these. They are in your data booklet. Once you have the hydrogen ion concentrations, you can figure out the hydroxide ion concentrations using this KW equation for the ionization of water, the dissociation of water. So all you have to do is take your 1 times 10 to the negative 14th and divide it by your hydrogen, 1 times 10 to the negative 4th. That gives you 1 times 10 to the negative 10th. Times 10. Sorry, my Apple Pen is not doing the best today. Okay, molar hydroxide. For the second situation where the pH is 11.55, it would be 1 times 10 to the negative 14th divided by 2.82 times 10 to the negative 12th. So that equals 3.55 times 10 to the negative 3rd molar hydroxide. So there you go. So you can see definitely the one with the more acidic pH has a much smaller concentration of hydroxide, which makes sense. It has more hydrogen than hydroxide ions. So acids and bases can be classified as strong or weak depending on how well they dissociate into these hydrogen ions. So something that is a strong acid is going to dissociate more completely than something that is a weak acid. So it depends on how strongly they affect the pH of the solution. Remember, the more hydrogen ions in solution, the lower the pH, and the more easy it is to dissociate into these hydrogen ions, the lower the pH is going to be. So strong acids are completely ionized in aqueous solution. So they break apart completely into their protons and their anion. So therefore the reaction arrow, instead of going both ways, is going to only go one direction to show complete dissociation. So these are really good proton donors. They do not want their proton, okay? So therefore their base, their conjugate base, the chloride, are weak. They don't want to accept protons. They're like, no, I'm good by myself, okay? So strong acids have weak conjugate bases. So this hydronium can donate its proton to chloride, but it doesn't do a good job of it because chloride's a super weak base. So they're like, nah, I'd rather stay alone. So weak acids are reversibly ionized in aqueous solution. So we indicate this by the arrow, which I mentioned before, the equilibrium arrow. It's called a double harpoon arrow. So you can see that it goes both ways, so that this acid, this is ethanoic acid, it can donate its proton to water to form hydronium and ethanoate. However, it's very weak. It doesn't do a very good job at getting rid of the proton. So as soon as it donates it, it can't accept it back. So this weak acid has a very strong conjugate base. This ethanoate ion over here is actually really strong and it wants to accept that proton back. So therefore, the amount of hydrogen ions in solution isn't going to be as high as for something like hydrochloric acid because this strong-ish conjugate base wants to take back the proton, okay? So there's going to be less hydrogen ions in solution comparatively. The same can be true for strong bases. Strong bases completely dissociate into metal ions and hydroxide ions in solution. So on the other hand, weak bases react reversibly with water to form hydroxide ions and relatively strong conjugate acids. So for example, we have ammonia, which is a weak base. It is acting as a base because it accepts that proton from water to form ammonium and hydroxide. And of course, it's a base because it's resulting in hydroxide ions in solution. That is the definition of something that is basic, according to Arrhenius. So whenever it accepts that proton, this is the base here, right? So ammonium is the conjugate acid. Now, ammonium is a relatively strong conjugate acid, so it does not like to have that extra proton. It's like, I'm kind of uncomfortable having this, so I want to give it back. So it gives the proton back to hydroxide, so there's less hydroxide in the solution. So therefore, compared to sodium hydroxide that does not grab that proton back from, or does not take that proton back from something else like water, this hydroxide gets that proton from the ammonium ion, and so there's less hydroxide in solution. So therefore the pH is going to be a little bit lower than something like sodium hydroxide. Weak bases do have pHs above 7, but they're usually about like 8 or 9, whereas a strong base will be something more like 12 or 13. So you can see that ammonium. So you can see the ammonium ion giving the proton back to hydroxide right there. So how do you distinguish between these strong and weak acids? Well, because strong acids as well as bases have a higher concentration of ions in solution, either, hydrogen ions or hydroxide ions, they have higher electrical conductivities. So if you put a conductivity meter in a strong versus a weak acid, you would see much more conductivity in the strong acid. So for example, this is ethanoic acid, a weak acid, and this is hydrochloric, a strong acid. So you can see there's enough current in the solution of hydrochloric to light up the light bulb, whereas the ethanoic acid does not have enough current. Also, strong acids react with metals more strongly than weak acids at the same concentration since they're completely ionized. So acids and metals like to make hydrogen gas. So a lot more hydrogen gas is going to be released when you mix it with a strong acid as opposed to a weak acid. So therefore, strong acids produce more heat and produce more hydrogen gas at a faster rate compared to weak acids. They also lower the pH of a solution more. So they're going to have a lower pH, like pH 1 is a strong acid, that's about hydrochloric acid. Whereas a weaker acid, like vinegar, which is acetic acid, it's got a pH of about 3, which you might think is strong, but compared to a strong acid like hydrochloric is not. Remember, that's 100 times less hydrogen ions. So the last thing I want you guys to do is to distinguish between strong and weak acids here. Okay, so we have nitrous acid, which is a weak acid, and then we have nitric acid, which is a strong acid. I want you to write equations for the dissociations in solution. And remember, strong acids dissociate completely, whereas weak ones do not. And then if you put a small piece of magnesium ribbon in nitric versus nitrous acid at the same concentration, describe 2 observations you would see that allows you to distinguish between which one's strong and which one's weak. All right, guys, that is it for this lesson, and I will see you in class tomorrow. I hope you have a great rest of your day. Bye.